guys. Today I will discuss you about something which is related to the digital circuits. So in this topics are AND, OR, inverter circuits, how to represent under inverter circuits, and another thing is OR and inverter. Okay, so AND or NOT is a basic circuits in the digital, which is the representation of AND is this. So OR it will be represent with, so it will may have any number of inputs, that is not necessary it should have a 2 input, should have any number of inputs. So suppose you can see the OR gate which have 3 input. Okay, the NOT gate representation is this one. So you have to throw with symbols with the basic gates. Okay, now the AND or NOT is nothing but sum of products representation. There are two representation styles of any logic. So one type of logic is sum of products, which means it will be like this. So AB plus CD plus DE, that means this is a product. So this is a product, another product, this is another product. So in between the products we are summation. So sum of products, this one product, another product, we are summing the products. So sum of products. So this type of representation of any function is called sum of products. So come to the OR and NAND. So same gates, but the representation will vary. So this is product of sums, product of sum. Okay, so here we are doing product, and sum is the our expression or literals. So here I am doing summation. This is one sum, this is another sum. You can have another terms also, no problem. So in between we are doing AND operation. So this comes under POS, product of sums. So two styles, one is sum of products, another one product of sums. Okay, so you understand. AND or NOT comes under SOP form. So here they give you some, if this is the sum of products and it is inverter. Here I use two styles of inverter. One is I can use inverter like this, and A bar, or I can use A bar. So both are represents the same, it is a inverter. So this coding, this function can be represented in the digital circuit like, so AB AND gate, CD AND gate, D AND gate. So AND is over. Okay, now it is OR. So we are doing OR gate with the outputs. So next OR gate is on. Next we have the inverter. So this is the inverter representation. So we are doing inverter. So sum of products is representing the AND or NOT representation. Okay, it comes here. So here I have a OR gate and I have a NOT gate, which is nothing but is equal to this NOR gate. So this bubble is fed to it, this is NOR gate. So here if you see, there is a OR and NOT which gives a NOR gate. So this form is becomes AND and NOR. So AND and NOR logic it comes. Okay, so you know AND or NOT falls on the SOP, first point, and second point, how to see the function. The function is always in sum of products. So third one, you know how to represent the function into digital circuit. So later you can convert this function into NOR gate. That's also not problem. Then your circuit becomes AND and NOR. You will see this one. Okay. So next is OR and NOT. we have already discussed that this comes under POS, product of sum. So as I said, so it will be the function represent A plus B, C plus D and inverter. Okay, so if I represent, so you have to learn how to represent this in the digital form. As I said, A plus B is represents OR gate, C plus D represent OR gates. In between there is an AND gate. So AND gate represent AND gate, and there is an inverter. So if you see that OR and NOT will represent OR product of sum. So this is that. So you have to think of 3 points you have to gather. One is the OR and NOT will represent product of sum. The expression will be, there will be a AND gate between the sum of product. Okay, how to represent that in a digital. So here also this is a AND gate. So if there is an inverter after that AND gate, it is equivalent to the NAND gate. Okay, so as I represented AND and NOT, it gives you NAND gate. So the circuit becomes OR and NAND. So you have to remember that. So every AND or NOT will give you a AND NOR logic. So every OR and NOT will give you a OR NAND logic. Okay, so now you will see how to do. If you give the example, so you can see. So this is an example which I taken for both to do and OR and inverter and OR inverter. Okay, first I am doing OR and inverter. Okay, so I know that if there is a x, y, z plus, this is my function which I gave. So by by seeing the equation, you came to notice that how to do. So what is the result? You know the result. Okay, I will write here. So you know that this is your function. So if I want to represent, okay, in, as we discussed in the earlier, if I write into a okay, OR and NOT, it is nothing but product of sum. So I am doing the first is OAN or inverter. Okay. So I know that my answer should be like sum of these things. That means sum. So this is one term. This plus will go here, AND gate will convert it into plus, and plus will convert it into AND gate. And there is an inverter. So this is my answer for first one. Similarly, if I convert the same thing in the first form, which is called AND or NOT form. Okay, it is simple because it is given already in sum of products. So the thing is only remainder is left, inverter is the left. So your answer should be like so you have already product of sums, so inverter is missing, so your answer should be these two things. So we will try and work it out how the conversion will take place. Okay, how it is converted to first form and second form, how you derived the things. Okay, so first method we will use normal simplifying expression. Okay, this second method we will use K-map. Okay, you understand? So if they gave you some expression, then how to convert it? Okay, so you can convert simple expression, you will get second form AOI, OAI, another one you can get AOI. Okay, so this is K-map. So I will discuss So we will start with first one. So first one, as we discussed here, there is an example. So I taken the same example. So this is already in the given form is in SOP. So we need to convert an POS. So apply De Morgan's law. So before doing these things, you have to thorough with De Morgan's law. What is De Morgan's law? How they are implementing. So I wrote here simple example that you can take the double complement. You can share that double complement with AND gate. That means you can say easily to understand. Okay, if there is an A dot B. Okay, if there is an A dot B that have a complement. Okay, so that will complement into, it will share the complement and the AND gate will convert it into OR gate. So this is it. So say reverse also possible. So if you have such thing, you can convert into this thing. Okay, so if I have like this, so you can convert into AND gate means A dot B dot D. Okay, same thing can be possible by reverse. So these are two things De Morgan's give. Okay, so we will discuss, we will use it in the expression. So here that is the first thing. Here they gave some expression. Suppose if you take this is A, this is B. Okay, no problem. Okay, so what you are doing double complement. So A plus B whole bar. So suppose you can think like this, A plus B whole bar. Okay, so what I say De Morgan's law, A plus B whole bar, that means you can split that into a OR gate converts to this one, and you can one bar you can use and one bar you can keep remain constant. So one bar I said how to one bar will split. So the same thing it will happen here. So one bar is splitted to A bar then B bar. Okay, similar this is second one. So I said here this is AND gate. So we think about only this thing, this product. Okay, so this product is like A dot B dot C dot bar. Okay, like that. So what it will happen, it will convert to, so this is also bar, this is also bar, this bar. So X plus Y bar, this bar. Okay, so the OR gate will convert into, it will remain the same because we doing the bar only this thing. So this is also same thing. So it converts it into X bar, Y bar, Z bar. So here you think that there are two inverters. Okay, so inverter cancel each other. So I wrote this expression as X plus Y plus Z, and this expression as X plus Y bar plus Z bar. So here it comes OR and NOT gate. NOT gate is nothing but the inverter, whole inverter is NOT gate. We represent this in the same structure as we thought how to represent the structure. So OR gate comes from the first. So X plus Y plus Z, and another this. So AND gate is the NAND. So I said you can use it as a NAND. So OR and NAND. So similarly you can do this is for exercise. Okay. So this is second one which we discussed in the earlier. Is nothing but this one we discussed because you will get OR and NAND. Similarly we got OR and NAND. So first one we will discuss now. I said what is the method to apply for second one. It is nothing but simplifying technique. This is called the simplifying technique. So we will get the required answer. So we got the first one. So first one we got by simplifying the technique. Okay, next is K-map. Okay, so this example we will do with using K-map. Okay, So before that, you have a prerequisite to study this thing. So equivalent gates. So I represent like this. If there is a NOR gate, this is nothing but NOR gate, is equivalent to bubbled AND gate. Okay, this is bubbled AND gate. So similarly, NAND gate. NAND gate is equivalent to bubbled OR gate. So you have to understand these things before going to next. Okay. So here you will go for another example. Okay. Okay. So as we discussed last thing, last thing is this structure we come with the second one. So similarly, same structure, it is NAND. That means both are same structure. What we got the structure is OR and NAND. So I represented this thing in OR and NAND. So as I said that NAND gate equivalent is, I said bubbled OR gate. Okay, bubbled OR gate. So you can convert this NAND gate into bubbled OR gate. So the bubble is given to OR gates. So like this. So this OR remains same, but the bubble is getting fed to the previous. That means successive gates. So here it will get NOR gate. NOR. So it becomes NOR and NOR. NOR and OR. Before that it is like OR and NAND. It is converted into NOR and OR. So we know that we use simple technique called equivalent gates. So bubble, that means NAND gate is equivalent to the bubble OR gate. That bubble is given to both OR gates, becomes a NOR gate, and OR gate remains keep constant. Okay, so we converted in the first. So we are going to next technique is called AND OR inverter. So I said for this technique you have to use K-map. So you will get simple because the given function is already in SOP form. That means sum of products only. But there is no inverter. So we need, our equation is like inverter. So we need inverter. But they gave only this thing. So we need inverter. So for that we are making K-map. So how to get that logic? Okay. So simply, so if I want a inverter here, that is equivalent to F bar only. So if I found F bar, it is nothing but inverter only. Okay, understand? So here you can see, if I found F bar, it is nothing but I can get the equation directly. So because it is equivalent to F, so this bar is shifted to here, it will mean nothing but it is F bar. So here I am finding F bar. Okay, so F bar I am making into a K-map. Okay. So this is a K-map. So before that you have to know what is K-map, how we can draw everything. So this is a 3 variable K-map because there is 3 variables X and Y and Z. So I put first one in X, Y, Z. So X is 2 possibilities 0, 1. Y have 4 possibilities 0, 0, 0, 1, 1, 1, 1, 0. Okay. So here it is nothing but the first term is nothing but 0, 0, 0, 000 because it is X bar, Y bar, Z bar 0, 0, 0. So 0, 0, 0, it is the first block. So I put 1. So next one it is 1, 1, 0. So 1, 1, 0, it is falls under this one. So I put 1. So remaining blocks I filled with zeros. Okay. So if you find out expression for the F, you can group 1. If you are finding expression for F bar, you have to group zeros. So here maximum possibility to make a group is 4, so I can group maximum 4 zeros at a once. So I made one group, but remaining 2 zeros are unleft, so I'm making this is 2, because I can't do 3. I can do 4, 2, 8, 16. So 4 I did, then next possibility only 2, that is with 2, because this is not covered, so I am doing 2. This is also not covered, this is 2. Okay, so see how I am getting the equation from K-map. So first start with big box. Okay, 4 box. So 4 box, you see left and right. Okay, left and column and row. So coming to the column, it is axis 0 and 1 for this big box. So 0 and 1 cancel each other, so there is no x term. Okay, leave it that one. X is not there because 0, 0, 0, 1 cancel. So come to row. So row has 2 terms, 0, 1, 1, 1. So this y has 0 and 1, so it will cancel. But z has the constant 1, 1. So z will survive. So I am taking the big box will give z only, because by column x is cancelled, by row y is cancelled. Only z is survived. So z is comes in the output. Then you have to put plus, because another boxes are also there. You have to find out that equation also. This is the term for big box. Okay, this is another one. So for that we have to keep plus symbol. So coming to the this box, these two blocks. Okay, so you have to see, as I said, column is x is 0, because there is no 1, because it is falls under only x is equal to 0, because it is only have x is equal to 0. So x0 means x bar. If it is 0, x bar. If it is 1, x. So my x is 0, so I am getting x bar. So I am getting x bar. So come to row. This has two things, 1, 1, 1, 0. As I discussed earlier, y is not changing, y is 1, 1 only, but z is changing 1 to 0. So z will cancel, y will survive. So already we have x bar, now we have y. So the expression is x bar y. This is for second block. Similarly, you can check this block also. This block now is x is 1. That means there is x in our equation. And you see the row which is 0, 0, 0, 1. So y is 0 to 0, it is surviving. That means there is 1. Z is 0 to 1, so z is cancelled. So y is 0 means it is nothing but y bar. Okay, so x bar, y bar. So this is the final equation for f bar. Notice that it will be f bar because we are grouping zeros. So f bar is equal to, we are getting this thing, or otherwise you can change that f bar to here. That means inverter. So we got the final equation, required equation. So you can see our required equation is x bar, y bar, y bar. So by doing K-map we got the required equation. So you know how to represent the equation. It is AND gate and a OR gate between them and inverter. I said this is an NOR gate. I said NOR gate equivalent is bubbled AND gate. As we discussed in the earlier circuits, NOR gate equivalent is bubbled AND gate. So come to this, so bubbled AND gate. Okay, so if you distribute these bubbles to each and every gate previously, so it will get AND. Okay, but here there is no such gates, so it is nothing but bubble is nothing but a inverter. So if there is no gate in my line, you can represent it as a inverter. The bubble is nothing but a inverter. So only we are getting NAND gate. So the bubble is distributed over this one, so you are getting AND gate, NAND gate. So like here you have to do example. Okay, so I summarize these things. Once again you hear listen carefully. So first thing is there are two methods to represent any logic thing. One is sum of products, another one is product of sum. So if they are given some example like this thing, we have to convert into, if we convert into both forms for the same form, that means product of the sum of the product, we have to use k-map. If you use for another form product of sum, you can go for simplification like this, so we can get the simplified equation. So before that you can assume that this is the output like this. You can assume that if they give some equation, you can assume this is the output, this is the output. So follow some method how to do both of these. Okay, don't forget the De Morgan's law, it will be useful for simplification only, and for k-map you can use for that thing. Okay, so after once you got the equation, you draw it in a first normal thing like this. So first draw in the normal, then you convert it, and you can say what is that resultant. Okay, so it will be first of all OR and OR for this thing. So second you will get here NAND and AND. Okay, don't forget these two things from the two implementation techniques. Hope it is useful to you. Thank you.